Here are 6 numbers. Can you find 3 of them that add up to exactly 0? Take a moment. This one works. -1 plus 0 plus 1 equals 0. But here's the tricky part. We don't want just one answer. We want every unique triplet that sums to 0. And duplicates are not allowed. In the last video, container with most water, we moved 2 walls inward from both ends. Same idea today, but with a twist. First, we lock one number in place, then we search for the other 2. The obvious way is to try every combination. Pick one number, then another, then a third. That means 3 nested loops. For a small array, it works. But as the input grows, the number of checks explodes. This is O of n cubed, and for interviews, that's too slow. Now the trick that changes everything. 3-sum looks like a 3-number problem, 3 numbers to juggle at once. But watch what happens when we fix just one of them. Call the first number A. Our equation is a plus B plus C equals 0. If A is locked in place, we can move it to the other side, and it becomes B plus C equals negative A. Look at that. We've just turned a 3-number problem into a 2-number problem. This is 2-sum, the problem you may already know. Say we fix -1, then negative A is positive 1. So now we only need 2 numbers that add up to 1. Suddenly it's simple. But how do we find that pair quickly? This is where sorting comes in. First, we sort the array from smallest to largest. Why does that help so much? Because sorting gives our 2 pointers direction. We put 1 pointer on the left, at the smallest number, and 1 pointer on the right, at the largest. Now we add them up. If the sum is too small, we need something bigger, so we move the left pointer 1 step to the right. If the sum is too big, we need something smaller, so we move the right pointer 1 step to the left. Every single move is deliberate. We never waste a step, and we never have to go backwards. Let's walk through the whole thing on a real array. After sorting, we have -4, -1, -1, 0, 1, 2. We loop a fixed number, I, starting at the very first one. Left goes just after I, and right goes to the end. First, I is -4. That means we need the other 2 numbers to add up to +4. Left is -1, right is 2. -1 plus 2 is 1. Way too small. We need something bigger, so we move left to the right. Still too small. In fact, with -4 fixed, no pair can ever reach 4. So -4 gives us nothing, and we move on. Now I becomes -1. We need a pair that sums to 1. Left is the second -1, right is 2. Together they make 1, and with our fixed -1, the total becomes 0. That is our first triplet, -1, -1, 2. We save it, then move both pointers inward. Now left is 0, right is 1. 0 and 1 make 1 again. Add the fixed -1 and we get 0 once more. Another valid triplet, -1, 0, 1. Now the pointers meet and we are done with this fixed number. Now the part beginners get wrong the most, duplicates. Look closely at our sorted array. We have 2 -1s sitting right next to each other. We already used the first -1 as our fixed number and it found its triplets. Now the loop wants to move I forward to the second -1. But stop and think. If we start a brand new search from this second -1, we will look for the exact same pairs and we will find the exact same triplets we already have. Same fixed number means the same family of answers. So the rule is simple. If this fixed number is equal to the one right before it, we skip it completely. We don't even start the 2-pointer search. And there are 2 more places duplicates can sneak in. After we find a valid triplet, the left pointer might land on another equal value. Skip it. The right pointer might too. Skip it. 3 small skips and no duplicate ever reaches your answer. Now let's build the solution. First, the plan in plain words. Sort the array, then loop a fixed number. For each one, use a left and a right pointer to search the rest. If the 3 add up to 0, save the triplet and skip duplicates. If the sum is too small, move left. Too big, move right. And one smart shortcut. If your fixed number is already greater than 0, you can stop because the array is sorted, so everything after it is positive too, and 3 positive numbers can never reach 0. Now here it is in Java. The first part, we sort, We loop the fixed number, we skip a duplicate fixed value, and here is that early break. Then we set left and right. The second part is the two-pointer loop. We add the three numbers and react. When the sum is 0, we record the triplet, then skip duplicate lefts and rights before moving both pointers inward. And here's the exact same logic in Python, split the same way. Sort and loop up top, the two-pointer search below. Notice how clean it is. Pause here if you'd like to copy either one. Before you go, 5 mistakes that trip people up. First and most common, forgetting to sort. Without sorting, the two pointers have no direction, and the whole method falls apart. Second, and just as important, not skipping duplicates. This quietly lets identical triplets into your answer, and it is the #1 reason a three-sum solution gets rejected. Third, moving the wrong pointer. Remember, sum too big, move right, sum too small, move left. Mix these up, and you will never converge. Fourth, forgetting to move both pointers after you find a triplet, which makes you record the same one twice. And fifth, reaching for a hash set to force uniqueness. It can work, but it is messier and slower than sorting with two pointers. So remember the recipe. Sort the array, fix one number. Use two pointers for the other two. Move based on the sum, skip duplicates, all in O of n squared. And the one line to keep in your head. Three-sum is not 3 loops. It's one fixed number plus one smart two-pointer search. Next, we take this pattern even further with trapping rainwater. If this made three-sum click, subscribe. It really helps. See you in the next one.